Okay, in the part 1 video for chapter 19 for AP statistics, we covered almost all of chapter 19. In this second part, this is going to be much shorter. We're just going to talk about one other thing that happens and just kind of summarize some things. The other thing is when you're in real life, if you're really trying to conduct an experiment or produce some sort of data that you can analyze to report a result, you usually have a choice over how many things to include in the sample. You can choose the sample size, right? But you should always do a calculation first to determine how big that sample size needs to be if you want to be able to report a certain margin of error, right? So it's not good to go to all the trouble of collecting a bunch of data, processing it, doing the analysis, only to find out that you could only report the answer within plus or minus 20% when you really needed it to be plus and minus 5%. It's better to find out ahead of time that you should have collected more pieces of data, right? A bigger sample size. All right, so if you have a desired confidence level and a desired precision up front, you can calculate the sample size to match that. Okay, we know that the margin of error is z star, which is the number of standard deviations times how big a standard deviation is, and the standard deviation is the square root of p hat q hat over n. So that means as long as you know the margin of error you want and the confidence level, then you should be able to figure out what n needs to be so that you'll be able to have that happen no matter what your p hat turns out to be. Okay? All right. So, for example, let's say that you're doing some kind of political polling and you're working for a candidate, and the candidate is planning a poll once to be able to estimate voter support within 3%. And they want to be 95% confident of that result. How large a sample is required? All right. So we don't know the p hat because we haven't done the poll yet, right? So we're going to assume the worst case p hat. We're going to assume p hat is 0.5 because that always gives us the widest margin of error. So if we don't know the p hat, you can assume 0.5 as a worst case value. Okay. So let me start with the formula for confidence intervals. Confidence intervals are p hat for one proportion, p hat plus or minus z star times the square root of p hat q hat over n. Okay, I can fill in 0.5 for p hat, and therefore q is 1 minus that is also p, right? If I want to do 95% confidence, off on the side, I could do a little calculation here that says for z-score, if I want to have 95% chance of being in the middle, there's a 5% chance left over, 2.5% here, 2.5% here. And when you do inverse norm with 2.5% below some boundary here, 0.025 with a mean of 0 and 1, you're going to get negative 1.96, so you throw away the negative. So I have to go plus or minus almost 2 standard deviations, right? So that's my z star value, right? So what I can do is say, all right, the margin of error is just this part, right? When they say within 3%, that's the margin of error. I'm going to abbreviate that ME. That's this part of the calculation right here. So that's the margin of error. So I really need that to equal 0.03. So I could write it this way. The margin of error must be 0.03. And because the margin of error is z star times the square root of p hat q hat over n, and that's got to equal 0.03. I can fill in that z star has to be 1.96 if I want to be 95% confident. And I can fill in 0.5 for p and therefore 0.5 for q. And then I can solve this because now I have an equation of algebra that I can solve, right? So what I would do first is I would divide both sides by 1.96. Let me do the steps here. If you divide both sides by 1.96, I'll show this because sometimes people mess up this calculation. 1.96. Then you'll get this. You'll get the square root of 0.5 times 0.5 over n equals 0.03 over 1.96, okay? And then I would square both sides. The next thing I would do is square both sides to get rid of the square root. So on this side, I would have 0.5 times 0.5 over n equals 0.03 over 1.96 squared. Okay. Okay, let me move this up here so I have more room, and then I'll bring that back down in a second. All right, so the next thing we would do is say, all right, let's multiply both sides by n. So if we multiplied both sides by n, they would cancel out on this side. And so I would have, let me swap this around. I'll have n times 0.03 1.96 squared equals 0.5 times 0.5. I just reversed left and right. And then finally, I'm going to divide both sides by this 0.03 1.96 squared. Okay, and so what that means is that my n is 0.5 times 0.5 divided by 0.03 divided by 1.96 quantity squared. And if you carefully plug that in your calculator, you'll get the value 1067.1. Okay. Now, I am going to have to round this up to a particular number because I want to know what n is, which has to be an integer. So you always round this up. Okay. We need to ask 1,068 people minimum this survey question if we want to be able to have our final answer be within 3% at 95% confidence level. So this kind of a calculation is referred to as a sample size calculation, right? And the reason we would do that rather than just say, you know what, just keep sampling and make it bigger and bigger and bigger, is that there is a cost associated with sampling, right? Whenever you increase the sample size, you end up spending more money. It takes more effort to process the data, right? So you don't want to go overboard, right? In fact, if I was going to conduct this poll, I would probably say I need to end up having asked this question of 1,068 people. I imagine that I'm going to get a lot of non-response bias. There's going to be a lot of people that are going to say, no, I don't want to answer your question. So to be safe, maybe I would ask 2,000 people, hoping that I get at least 1,068 to respond. Because as long as I have that, then when I go through my calculation with my data, no matter what p hat is, I'm going to end up within plus or minus 3% or less, and I'll be 95% confident of the results. So this kind of calculation is really important and very, very frequently seen on the AP test. All right, so that's called a sample size calculation. A couple of things. I want to draw attention to the fact that there's a difference between the confidence interval and the confidence level. So the confidence interval is the result of this computation. When you do the computation, you'll get, something like this. And this is the standardized wording that you have to use. We are 95% confident, or whatever your confidence level is, that between your lower end and upper end of, and whatever the thing is for the problem, like we're 95% confident that between 57 and 68% of all U.S. adults would say the death penalty applied fairly. So that's explaining the confidence interval itself. Okay. If you're asked to explain the confidence level, that's the 95% part. Okay. So this is the standardized wording. I'll use the same thing here. If we took many samples of size 537 and computed confidence intervals for each, then 95% of those confidence intervals would contain the true proportion of all US adults that say this is being applied fairly. So you have to make reference to this idea that the confidence level has to say that, every time if you were to do this experiment many times, you'd get a different p hat value. And each one of them would have a confidence interval. 95% of those intervals are going to contain the real value, and 5% will miss it. Right? So this is the standardized wording we know AP likes for that. Right? Something like this. If we took many samples of that sample size and computed confidence intervals for each, 95% or whatever your confidence level is of these confidence intervals would contain the true proportion of whatever it is you're analyzing. All right. Okay, just a couple things to be careful about. Be careful to state the conclusion correctly, right? We want to make sure we have an appropriate balance between margin of error and confidence, right? You don't want to do things like have huge margins of error so that you can claim to be 99% confident. Like, it's not very useful to say I'm 99.9% confident of something, but then your confidence interval is the answer somewhere between 50% and 78%. That's not going to tell you much, right? On the other hand, going the other direction where you can say, okay, I know that the answer is somewhere between 48% and 49%, but we're only, 40% confident in that result. That's not useful either. So you have to come up with some kind of a balance. The most common confidence levels are 90, 95, and in some rare circumstances, 99. Usually 90 or 95. 95 by far is the most commonly used. Okay. Okay, choose an appropriate sample size because it's always better to sample more statistically, but there's always a cost associated with it. And then don't forget to check the conditions, right? Every time you have to do that. Okay. All right, that's it for the second part. So you should have everything you need now to complete anything in the Chapter 19 required practice packet or extra credit practice packet.